Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 7th, 2025, just 2 days ago. This paper introduces a new framework for robotic navigation that can generate actions with an average inference time of only 0.27 seconds. The paper is titled StreamVLN, Streaming Vision and Language Navigation via SlowFast Context Modeling, and this approach allows it to navigate complex environments with impressive speed and accuracy. The authors tackle the challenge of helping an AI follow instructions by efficiently processing long video streams, using a hybrid memory system to stay responsive. Alright, so this first figure lays out the core architecture of the StreamVLN framework. You see the input at the top, a continuous stream of camera images. The clever part is its hybrid memory system. For recent events, it uses a fast sliding window to stay responsive. For older, long-term memory, it uses a slow updating process. This involves a technique called voxel-based spatial pruning. A voxel is just a 3D pixel, so if the robot sees the same spot twice, it prunes or discards the older view. This dual system is the key to maintaining speed while remembering the entire journey. So, to get that sophisticated architecture to work, the authors needed a very specific training diet. This chart breaks down that co-training data recipe. About 2/3 of the data is for Vision Language Action, or VLA, which specifically teaches the model how to link sight, instructions, and physical actions. This includes data from simulations and, importantly, corrective demonstrations from a technique called Dagger. That's where the model learns from its mistakes. The other third is general multimodal data, which helps the model maintain broad reasoning skills beyond just navigation. Moving to the results, this table shows how that training really pays off. It compares StreamVLN against other leading models on 2 challenging navigation benchmarks. The key metrics are success rate, which is simply reaching the goal, and success weighted by path length, a stricter measure that also rewards taking an efficient route. You can see that StreamVLN, especially the version with the extra training data, achieves state-of-the-art results with a 56.9% success rate and 51.9% success weighted by path length on the R2R benchmark. This table then digs into why the model is so efficient, with what's called an ablation study. It's an experiment that isolates one specific feature, that voxel-based spatial pruning we talked about, to measure its impact. The top row shows performance without this pruning, while the bottom row shows the results when it removes about 20% of redundant visual data. Counterintuitively, you can see that removing that data actually improves the success rate and the success weighted by path length. This proves that being selective about memory isn't just faster, it makes the model smarter. Building on that idea of smart memory management, this graph really drives home the importance of the model's hybrid memory system. It plots latency or response time against the number of steps in the journey. The key term here is the KV cache. A KV cache, which stands for key value cache, is a kind of short-term memory that helps the model generate its next action faster. You can see simpler methods, like the red line sliding window, suffer from huge latency spikes every 8 turns. But the blue line, representing the full StreamVLN system, remains consistently fast and stable, avoiding those disruptive spikes entirely. So this next table explores the sweet spot for that hybrid memory system. It's another ablation study, this time testing different sizes for the long-term memory and the short-term sliding window. We see new metrics here, like navigation error, which you want to be low, and oracle success, which you want high, and there's a clear winner. The configuration with a memory size of 8 by 196 and a window size of 8, highlighted in bold, gets the best performance across the board, achieving the highest success rate and success weighted by path length. So, putting it all together, the key takeaway is the power of this hybrid memory system. StreamVLN combines a fast, short-term memory, that KV cache we mentioned earlier, for quick, responsive actions, with a slow, compressed long-term memory for understanding the bigger picture. This design, especially with its smart voxel-based pruning of redundant data, allows the model to be both highly accurate and incredibly fast, even working on a real-world robotic dog. That's our roundup for this week. I'm Alex. Thanks for tuning in.